Good morning, everybody. Welcome back. No, not welcome back. Well, hopefully you've had a day to get used to it. I'm still not used to being here. I'm kind of still on spring break mentally. What happened last year? I don't know. I probably should have waited to grade the exam until the end of my spring break. I started off my spring break feeling mildly depressed. But I posted those grades, and I did set out that announcement that redemption happens tomorrow, right? So there'll be more details tomorrow. But basically, I'm going to give you a chance to improve your grade on that test score. So don't miss tomorrow, right? What you will not be doing is taking the test again, right? What you will be doing is working the same problems again with your friends and neighbors and buddies in lab, right? And with the goal to give me a perfect exam at the end. And if it's perfect at the end, there's an alternative scale, a hidden scale that I have for improving your grades. So again, more details on that tomorrow. You don't want to miss tomorrow. I think what's going to happen tomorrow in lab, I had scheduled chapter 10 lecture. We'll see how far we get today. But if I still have chapter 10 lecture to do, then I will finish that up. And then we will do the fixing of your test grades project. So I'll kind of hold off on your questions about what's going to happen with all that till tomorrow when I have more time to talk about it. Let's see. We have 6 weeks, 6 weeks left. Chapter 10, chapter 16 and 17. So realize that you can see the schedule on Canvas. We're skipping chapters 11 through 15 because that's thermodynamics, and we're going to do that at the end. So we're going to combine chapter 10, which is simple harmonic motion, with chapters 16 and 17, which is waves, the application of simple harmonic motion. And then we'll come back and deal with the thermodynamics to finish the end of the chapter. So chapters 10, 16, and 17 are your next exam, which takes place 2 weeks from tomorrow. And then we have thermodynamics and your final exam, and that's it. So, hang on for the ride. Do note that I'm tossing out sections 10.7 and 10.8 for this chapter. All right. This is the final toolbox. Really, I mean, you can consider thermodynamics, I guess, a different toolbox, but it's so different from mechanics anyway, it doesn't count. We've done kinematics, energy, Newton's laws, and momentum. The fifth toolbox of physics is simple harmonic motion. And it's best described by just showing you what it is. Okay? This motion right here is completely different from the kinds of motions that we have been studying so far. Prior to this point, a lot of what happened was a car would accelerate or a car would slow down. It would move in one direction. Or, in the case of a collision, maybe we'd have a change in direction. But in all of those cases, we assumed that the acceleration was constant. And if it wasn't constant, then we did energy, which didn't care about the acceleration in the first place. This motion right here has a lot of things going on. Just a ton. So let's try and describe what's going on here. Let's introduce you some terminology and vocabulary that we use to describe this kind of motion. It's simple because we're not going to do friction. It's harmonic. What does harmony mean? Balance or blend in music. In physics, it means something that repeats itself over and over and over again. And that's really what this motion is doing, right? I get it started, and it goes up and down, returning to its initial condition, right? It started down here, right? And then I let go, it goes up and comes back down. And this position right here is exactly the same that it was when it started, right? And then it repeats that motion over and over and over again. It's harmonic motion, repeated motion. It's simple because we're not going to worry about friction or any of the other twisting and turning stuff that we might see here, right? Okay? Now, this motion could start up here, right? I could drop it, start by dropping it, and I would have the same motion. Okay? I could start it right here, sort of at its middle point right here, just by sort of shoving it up, right? And I can get that motion to happen. What kinds of things in your experience do this? Either bounce up and down. Don't think like literally about springs, but what sorts of things are harmonic, repeat themselves over and over and over again? Waves do this, right? We're going to extend this idea of this motion into a traveling wave in chapter 16. What? Swing! Oh, sweet. I love the swing. Right? At the park. Okay. Swings do this. Yo-yos. Oh, mine go down and then fall off the string. Planets? What do you mean by that?
Because it continues to...
So, we've studied circles a lot, haven't we? Is circular motion a type of harmonic motion? Right, okay.
What about bearings?
Bearings, things that roll. Car tires. Clocks. Computer circuits. Light waves. Sound waves. Your car's engine. Does it go in a circle? Well, yeah, pretty much. Okay, it's got these pistons that go up and down in a harmonic motion, right? Which turns a drive shaft, which does turn in a circle. Your life, right? Okay. After this last exam, you're down here, right? Okay. We're gonna try and get you back up here. Stock market. The cycle of I need to go to work so I can make money. I need to make money so I can pay taxes and rent. I need to go to work so I can make money, right? Okay? So there's all kinds of cyclical processes in nature and in society. And we're going to take a stab at trying to describe what's going on here. All right. So features of a simple harmonic oscillator. Here we've got a mass on a spring. And we're going to do this vertically, only because that's the easiest way to set it up. Really, we are concentrating on a horizontal motion, okay, where we have like a mass that's on a frictionless surface that's attached to a spring. But it's really number one, it's hard to find a massless spring. Number two, supporting a spring in its horizontal configuration is pretty difficult too. So we're going to cheat. We're going to use my vertical spring here. I'm going to let you know that gravity doesn't matter, because it actually doesn't here. And you'll just have to trust me with that, but all of the concepts are still the same. We're going to mark a point there, and I didn't quite get it, did I? This is referred to as the equilibrium position. Okay? This is the resting position of this simple harmonic oscillator. Okay? The oscillator consists not only of the mass, but the spring that it's attached to. If I then pull the mass down to a certain point, okay, is it ever going to go down further than this point? No, it can't, right? Unless I give it an extra shove in the right direction, okay? So we refer, right, this is your 0 point, we refer to the point of maximum displacement as the amplitude, okay? And when I let go at amplitude, then this thing, yep, it's just about the same amplitude on the top side, right? Mine's not perfect. There's a little bit of friction and twisting and things that are going on here, right? Okay. But an amplitude, the furthest distance from the equilibrium position, is the same on both sides. Okay, that equilibrium position. All right. This oscillator has a period. We've talked about period before in terms of circular motion, how long it takes to go around. For this thing, it's how long it takes to complete one full cycle of its motion. So if it's starting down here, a full cycle would be start at the bottom, go all the way up to the top, turn around, and come back down. It's reached its original state that it started with, right? So that would be one cycle. If we started up here, what would be one cycle? Down and then back up again. If we started in the middle and I pushed on it from the bottom, what would be a full cycle? up.
The second.
And do I stop right there? That's only half. It's not the same condition. We started with it moving up at the center, right? Comes up and then starts coming. It's moving down now, isn't it? That's not the same condition it started with. It's got to get down here, turn around, and now it's back to the original state that it had. Okay? So we can actually measure that period regardless of where the oscillator starts in its motion, as long as we make sure that it goes through a complete cycle. The time it takes for that to happen is called the period, and we use the symbol T. There's another idea in here, unique to oscillators, called the frequency. Now, frequency is something you perhaps are kind of aware of. Our modern society and the gadgets that we use refer to frequencies sometimes. You may have heard of things like LTE and 3G and 5G in terms of our cellular phones. Those are all standards for communication on various frequencies of wireless signals. In the case of 3G and LTE, those signals have, I think are anywhere from 800 megahertz to 2.4 gigahertz. Your Wi-Fi in your home, the Wi-Fi coming out of that access point right there, those are also 2.4 gigahertz. Hertz as a unit is a unit of frequency, and it's the number of cycles per second. So when we say that the Wi-Fi is communicating at 2.4 gigahertz, how many times is that signal repeating itself in 1 second? What's a giga? Yeah, it's a lot. It's a billion. So that wireless access point is giving off a signal that oscillates 2.4 billion times per second. That's how much you need in order to get your Facebooks and your YouTubes and your Snapchats and everything else. Okay? So we have, for this oscillator, a frequency would be the number of times this thing completes its full cycle every second. So period and frequency are opposites of each other. They're inverses of each other. Period, time it takes to do 1 cycle. Frequency, the number of cycles in 1 second. And I'll write all this down on the screen in a second. Okay? So let's measure the period of this thing. Let's see. 1/1000. Okay, it's about a second, right? Okay, so if the period is a second, 1 second, how many times does this thing complete a cycle every second? What? Right? Okay. But let's pretend that this thing took 10 seconds to go from bottom to top and back down again. Okay. So if the period is 10 seconds, how many times does it complete its motion per second? 1/10 of its motion, right? However, if the period were 1/10 of a second, right, it did it really fast, then how many times could it complete its motion in 1 second? 10 times, right? That's where frequency and period are related to each other. So what I want to start doing on the screen here is writing down a toolbox. And the nice thing about simple harmonic motion is that we physicists have figured out all of the tools for this toolbox. And we understand these tools so well that, in truth, when a physicist doesn't know what something is, we observe something going on in the universe, right? And we go like, oh, well, how does that work? Our first reaction is to treat it like a spring. Doesn't matter if there's not a spring there, right? Okay? So the best example of this is, what's an atom? Way back 1893, well, even prior to that, but really 1893 is where it really got going. What's an atom? I don't know. Let's figure it out. Okay, let's treat it all like springs. When you do that, when you treat atoms like springs, what you get is quantum mechanics. Okay? So it can lead you into some really bad roads. But engineers will treat things like the bumpers on cars as springs, right? And now, is a bumper a spring? You wish, right? No, okay? what a bumper does is it just sort of compresses, right? If anything, it only ever does a quarter of a period of any kind of, it doesn't oscillate, but it just sort of crushes, right? Well, because harmonic oscillations, harmonic motion is so well understood, we will just run to that, say, okay, it's only a quarter of a period, weak, weak, and treat it like a simple harmonic oscillator for that long. All right, let's talk about some other things that are going on with this oscillator. Where is it moving the fastest? In the middle? Where is it moving the slowest? At the end. All right. What force is causing the motion to change? Name the object that's causing the change in direction. It's the spring. Okay? I know you think it will, gravity too, but we're going to ignore gravity. Okay? It's the spring. What kind of forces do springs exert? Glad you asked. This is called Hooke's law, Hookes, after the British guy that first wrote it down. I have written it without its characteristic minus sign. Matter of fact, your book does it twice. They write it with the minus sign, and then they write it without the minus sign. Now, I can put the minus sign in here. I wouldn't do this if I were you, but I'm just going to drop it in there temporarily. I'll get rid of it in a second. The reason you'll see this minus sign, you'll see it in textbooks, you'll see it on the internet, you check wherever you're going, right, okay, to get your information. You'll see them drop that minus sign in there, and then mysteriously it will disappear later on. The reason that minus sign is there is to remind us something about springs. X is the distance we have pulled the spring from its equilibrium position. When it comes to springs, you are not allowed to pick 0. 0 is the equilibrium or resting length of the spring. In this case, right here. When I pull it down 5 centimeters, okay, I'm pulling down, right? I move the spring into the negative x direction, right? But what direction is the force of the spring acting? Up or down? Spring's trying to pull it up, right? But if I compress the spring, I move the mass into the positive x position. What direction is the spring doing? Down. That minus sign right there in Hooke's law is a reminder that springs always oppose the direction of stretch or compression. When you push on a spring, it pushes back in the opposite direction. So that's why it's there, but in reality, when you are writing down the force that a spring exerts, don't use the minus sign. Because what we're going to do is we're going to have a free body diagram. We're going to show the direction on the free body diagram, and we have handled the direction. We don't want to double correct. We don't want to do the direction again, right? By putting in the wrong things. So just be aware of that. Physicists play really fast and loose with minus signs sometimes. We add them in when we need them, and we take them out when they're annoying and all kinds of stuff, and it looks like bad math, and it is, but that's okay. It works. That's always our justification. Universe does it, so why can't we? So you'll often, though, see when there is a minus sign, you'll see it kind of written with its vector notation to indicate what's going on there. But like I said, I got to be careful with that, right? The magnitude of the force that a spring exerts is equal to K times X. But what's K? How much force does a spring apply when it's sitting at its resting position when X is 0? 0, right? When X is 0, force is 0. Okay? You only get forces when you are outside of that equilibrium position. K, it's called the spring constant, it has units of newtons per meter, tells you how stiff your spring is, kind of how powerful it is. A really stiff spring will exert a lot of force in a tiny amount of compression or stretch. Whereas a real floppy spring, a loose spring, will have a low spring constant. So Slinkies, those toys, really low spring constants. Jello, really low spring. Yes, Jello is a simple harmonic oscillator. The springs in your car's suspension, very stiff, supporting a lot of weight, don't want a lot of motion, want to be able to apply a lot of force for very short displacement. Okay? So that number, the bigger it is, the stronger, the stiffer the spring is for a given compression or stretch. All right, so I've given you the definitions of frequency and period. We've talked about the forces that springs apply. But I believe it's really important to point out here that Newton's second law, right, applies. And if we, here, let me not draw that on the iPad screen. Let me draw it on the board because I'll draw the result on the iPad screen. Okay? We've got Newton's second law, right? And the only force that's acting on our spring over here, because we're going to ignore gravity, right, is Hooke's law, right? And, okay, technically, the direction of the acceleration and the direction of the applied force are going to, well, let's do it, okay? If the spring is moving up, it has positive x position. But what direction is the acceleration? We are going from its fastest speed at the equilibrium position to 0 speed, aren't we? So what direction, everybody point, what direction is the acceleration? It's down, right? It's moving up. It has positive position, but its acceleration is down. So I better make sure that my acceleration and my position vectors are being in the opposite direction. All right, well, solve that for acceleration. What do I get? I get minus k over m times x. So what that statement is right there is a way for us to find out what the acceleration is at any position. Where is this thing not accelerating? Not at the ends. Only at 0. Right? When the position is 0, the acceleration is 0. When the position is at an amplitude, then the acceleration is going to be the biggest it can be. And where is the amplitude? At the ends. Why is the acceleration biggest there? Well, what's it doing up here? Changing direction. Right? The velocity's gone to 0. But the acceleration's huge, right? It's going from one direction to another. Same thing's going on down here, right? So this is really the first case that you've been exposed to where the acceleration is not constant. The acceleration is changing everywhere. The acceleration depends on how much this spring is stretched or compressed. And so this is actually a really complicated kind of motion. It's nice and simple in one sense that we know what that acceleration and position function looks like. But when we try to solve for the acceleration, it's going to depend on where it is. Which means that our regular kinematic equations don't work. Kinematic equations we know and love deal with acceleration always being the same. When you hit the brakes on the car, we say it has exactly the same amount of acceleration everywhere along the motion. But here we just simply can't say it. Not even physicists know it's about the same. No, we can't do that. It's really different. The good news for you is that I'm just going to give you the punchline. The bad news for physics majors is that they have to go figure out how this works. And the answer is differential equations. Now, I don't think any of you have to take differential equations, right? In your majors. Differential equations class is one of the best math classes in the university. It's so good that I forgot all my other math when I took it. It was so like, right? But you get, we don't do calculus in here. And there's so much I could talk about, and I'm going to avoid it, but let me just give you 30 seconds. Acceleration is the second derivative of position with respect to time. Because velocity is the first derivative of position with respect to time. You take the, okay? So you've got a second derivative on one side, and you have a position function on the other. And the only way to solve differential equations, I went through an entire 2 semesters of this. The only way to solve differential equations is to guess. That's it. Don't let any mathematician ever tell you anything different, okay? Because really, all they're teaching you in differential equations is how to guess correctly. That's it. All right? We have all these fancy methods, method of variations, method of integrals, blah, 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 method of just guess, okay? You want to guess a solution, a function, that when you take its second derivative, gets you right back to the function you started with. I think you've had enough calculus to know that there's really only 3 functions in the universe that do this with any kind of periodicity. When you take a derivative of something, you get exactly the same thing back. What function is that? E to the x, right? You take derivative of e to the x, you get e to the x. Take the second derivative, you get e to the x. Third derivative, e to the x is a favorite in terms of guessing differential equations, right? But it's not e to the x. Okay, it's a little bit different. We're taking 2 derivatives and getting back to the same thing. Is there a function that you know about that describes this motion? That when you take its second derivative, you get the same thing back with just a minus sign difference? Sine and cosine. Right? So it should come as no surprise that what I'm about to write down will have sines and cosines in it. It comes about because of the fact that acceleration and position are linked together. And the way to describe what's going on is through these functions that have this periodicity to them. So I'm not even sure these are in your book, but I'm going to lay them out because they're pretty much everywhere else that talks about simple harmonic motion. For example, our position as a function of time equation. You can actually write these down with either sine or cosine. It doesn't matter. Okay? If you start with cosine, then when you write down velocity, what you're going to do is you're going to have sine. And then acceleration will be back to cosine. Now again, I'm not allowed to show you the calculus where these things come from. Okay, so you can take that to the bank right there, right? And yes, that is an omega that's sitting down inside of those functions. But basically, what those equations let you do is figure out how fast is this thing going 3 seconds after we let go of it? What's its position 10 seconds after we let go of it? What's its acceleration 2.3 seconds after we begin the motion?
The mass, do we take into account the mass of the spring?
Okay, not the mass of the spring. All of our springs are going to be ideal springs for this, right? And these toolboxes get more and more complicated as we start taking into account things like mass of the spring and blah, 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 right? But they're still already done, which is what physicists love to do. All we have to go is look up what happens when you have 2 springs, 10 springs, whatever, right? It's already solved. So it's a good question. Cosine, sine, cosine. But also you could do sine, cosine, sine. It kind of depends on where your mass is started. We'll stick with cosine. We'll try to start all of our motions. Cosine functions start at their maximum, don't they? Cosine of 0 is 1, right? So anytime you start an oscillator at an amplitude, you're using cosine, sine, cosine. If you ever run into a situation where an oscillator is starting at its equilibrium point, you're going to use sine, cosine, sine. I know, those of you that know calculus better than I do realize that there's a minus sign problem there. Okay? Don't worry about it. It's okay. Go for magnitudes. Okay? You could probably just take those minus signs out of there if you wanted to. All right. What else have I got for you? Oh, yeah. The fastest this thing can ever go is omega times A. That's because the sine of omega t, right, can only ever be between 1 and -1. So the fastest this thing is going is omega times A. The most acceleration it can ever have is omega squared A. And this omega keeps coming up, doesn't it? We know omega, don't we? What's omega? Angular speed. How fast something was going around in a circle. I have to admit something to you now. I've been lying to you. It's for your own good. It really is. Right? Kind of like those lies that we tell each other. Things like, it'll be okay. Or that dress doesn't make you look fat. The lie I told you is that omega was angular velocity. It's not. What are the units of omega? Remember, they were radians per second. Radian isn't a unit, right? This is an angular frequency. How many times does something go around per time, right? We didn't call it angular frequency back then because we didn't want to confuse you. We'd rather wait till now to confuse you, right? But this angular velocity is really angular frequency. And angular frequency and regular frequency have a relationship. They're related by 2 pi.
Is that f the frequency?
F the frequency in hertz. A hertz is a 1 over a second. Okay? Angular frequency isn't a hertz, it's a radian per second, because a radian isn't a complete circle, right? So there is a little bit of a difference there unit-wise, but when it comes to harmonic motion, I'm about to show you how the circles are involved here, right? When it comes to harmonic motion, angular frequency is the frequency that's most often used. You can see it's everywhere in the box up there. But even better, omega can be found if you know the spring constant and the mass of the oscillator.
What's the oscillator?
Yeah, the thing that's on the thing. So there's a lot of boxes here. This equation I would actually write as omega squared x minus omega squared x. Okay? Just to sort of make everything shorter and tighter. Okay? Yeah, we'll leave it at that for just right now. So this toolbox, right, all the things in the boxes here, all these equations that seem to be sort of be thrown at you, right? And, oh my gosh, there's a ton of equations. This toolbox comes with a lock on it. Unlike kinematic equations where the toolbox is free and open, you sort of reached in and grabbed the one that you needed, this one's locked. And to unlock this toolbox in every problem, what do you think the key is? What is showing up more or less everywhere? Omega. Do you see it? Omega is everywhere. So many simple harmonic oscillator problems are about, how do I find omega, right? If you know the spring constant and the mass, you're home free, right? But sometimes you only know the frequency or the period. And you've got to tease out what omega is from those things. So we do an example of this, right? Of dealing with this and combining it with other motions that we already know. But the idea behind these problems is it's all solved for you. Yeah, you've got to put these in certain orders depending on what they're asking for. But if you can find omega, you're done. right? Everything else is more or less just insert the omega in and let it all fall out. Okay, let's talk about circles.
What is A?
Amplitude.
What is that?
The biggest it is, the furthest the oscillator has gotten from its equilibrium position. It's a distance. It's the maximum distance. So, this picture's in your book, and there's similar pictures online and things like that. Forgot my math. Oh, did I? Yeah, I forgot my math on the screen. If we take this mass right here, right, this little ball, and we send it around in a circle, sort of a top-down view, and we shine some lights on a screen, and we just look at the shadow, okay, of this object moving in a circle. That's what they're trying to do over here. It's like on a record player, okay, it's going around. They're dragging a piece of paper. You can see the sine-cosine function, right? But if we didn't move the piece of paper, what would it look like on the screen as that thing went around? It would look like just like a line, and the object would be going back and forth in simple harmonic motion, right? Just like this thing right here, going up and down. I can think of it as a spring going up and down, just like you can see here physically, but I can also think of it as something that's circulating, right? Sort of looked edge on, okay? And seeing the shadow of that thing. So circles are intimately connected to harmonic motion, okay? Amplitude for a circular harmonic motion would be the radius of the circle, okay? Period. The time it takes to go around the circle. All of these things connect back up. So they're all there. All right, let's do an example. This is the Macau Tower, I think, in Malaysia. The world's tallest bungee jump. Okay.
And bungee jump?
Yeah. Bungee jump right there. Okay. Right. Very, very tall. Right. Yeah, zoom in right there. Oh, you took it. Okay. Right. Yeah, wave goodbye. Push him right. Yeah, don't grab on. Yeah, make sure it's connected. Good. Yeah, double check. It's good. Yeah, here we go. Now, why am I showing you bungee jumping? Simple harmonic oscillator, right? Okay, for a portion of the motion. Okay. Free fall first. The simple harmonic oscillation part doesn't happen until the bungee cord begins to stretch, right? Okay? Then the bungee cord's acting like a spring. But bungee cords aren't springs. As this thing comes back up, the bungee cord just goes slack, right? Unlike a spring, it can't push down. Here's the first person view. Upside down view of the world, right? Okay, so, and a disturbing thing is about to happen.
It snaps.
Yeah, you hear this click as he reaches up, right, to his feet and pulls on the string. He did not unclip himself. They need to unclip from one of the cords so that they can lower them down, right, successfully. So, let's do a problem, right, where we've got a bungee jumper. Okay? Now, like I said, we can only use simple harmonic motion for the part where the bungee cord gets stretched. And in setting up this problem and doing our visualization, we need to recognize that there's different things going on here, right? So we start with the bungee jumper up here, right? Okay? And then they fall, right, a distance, okay? At that point, the cord begins to stretch. And they tell us how far that is, right? 20 meters, right? So there's a 20-meter distance right here where the cord isn't doing anything. What kind of motion is going on in that 20 meters? It's free fall, right? We know all about free fall. We've done free fall before, so we've got that nailed, right? It's down here in this green portion, right, that we're going to have the simple harmonic motion. And they want us to find out how long it takes for the entire time it takes for the cord, once it begins to stretch, and then bringing the bungee jumper back to that original point. So what we're going to do is we're going to set 0 to be the part where the cord begins to stretch. We'll call that the equilibrium resting point of the spring. Okay? We're going to try and find out how long it takes for that to happen. Well, what sorts of things do we know? Oh, we know the mass, right? We know the mass of the thing that's sitting on the end of the cord, right? Okay? So basically, in the jump, right, the cord's up here. This is where it begins to stretch, and we're going to do the amount of time it takes, right? But they tell us that if you just statically hang the bungee jumper, right, the cord stretches how much? 5 meters. What's the thing we need in order to unlock the toolbox? We need omega. We can find omega if we know the period. Did they tell us anything about the period? No. Oh, are we going to need the period eventually? What are we looking for? Time. Oh, period has something to do with time, doesn't it? But they don't give us the period. They'll give us the frequency. We have the mass. So what's the other thing we need according to the toolbox if we want to find omega but we have the mass? The spring constant. But is there an equation that can give me the spring constant? Treat the bungee cord like a spring. Hooke's law tells me how much force, when it's applied, for a certain amount of stretch. If I know how far the bungee cord stretches, 5 meters, when a static force, the weight of the jumper, is applied to it, I know the spring constant. What's the force we're going to use? 70 times 9.8. We need the weight, not just the mass. We need the weight, right? So the force, the weight of the bungee jumper applied to the bungee cord, stretching it over 5 meters. So I can find my spring constant by using that force divided by that. That's going to be mg over that x. It's going to be 70 times 9.8 all over 5 meters. Did I figure that out? I did. 137.2 newtons per meter. So now I have my spring constant, which means I have omega. It's going to be the square root of 137.2, all divided by the mass of the jumper, 70, which gives me 1.4 radians per second. All right. What can I do with that omega? No, the question is, what can't I do with that omega? Because I can do just about everything, right? We can find the period of oscillation, right? Now that I have omega, the period of oscillation, are those related at all? Omega is equal to 2 pi f. F is the inverse of the period. So omega is 2 pi over the period, and the period is 2 pi divided by omega. That period 34.5 seconds. I'm having a hard time reading my writing. Okay. But now the question becomes, is that how long it takes for the bungee jumper to get back to the equilibrium position? If we start our stopwatch here, right? Bungee jumper's up here, falls, free fall, gets to here, begins to stretch, right? The bungee jumper only does half of the motion, right? Not the full period, but only half the period. So how much time does it take the bungee jumper to go from here down to here and come back up again? 2.25 seconds, right? So the answer to the question they're asking is 2.25 seconds, right?
Can you explain that last part again?
Yeah, the bungee jumper is in free fall all the way down to the point where they get to their equilibrium, where the bungee cord begins to stretch. Okay? They want the time from the point where the cord begins to stretch until it gets to the full extent and then comes back up to the equilibrium position. Because what's going to happen as soon as this bungee jumper gets to the equilibrium position? They're going to keep going, right? Momentum, all that kind of stuff. But is the bungee cord going to be pushing or pulling on them at all? No, bungee cords, they're like strings, right? They can't push on anything. They can only pull, right? So as soon as it gets to here, it's going to go into free fall again, right? So the actual simple harmonic motion portion is starting at the equilibrium, down to amplitude, and then coming back up to equilibrium. That's only half of a period. And after that, it does something else. And then it does half of a period, does something else. Does half of a period, right? Okay? So we're taking advantage of the fact that this thing only does simple harmonic motion for half of a period, but it's still enough for us to be able to figure out how much that time is going to take. If we tried to do it any other way, we would have had to go get calculus because the kinematic equations for that section are just nasty. We can find out what the amplitude is of this motion. This doesn't ask us for it, but we can find it. V max is equal to omega times A. So if we want to find the amplitude, how far the bungee cord stretches, what we really need to know is, what is the maximum speed of the bungee jumper? Does the bungee jumper reach maximum speed as soon as the bungee cord begins to stretch? Yeah, but they did it in free fall over 20 meters. How fast are they going? It's the answer. What's the answer? Other than 42? Square root of 2gh. Square root of 2gh, right? How fast is something going when it falls 20 meters? Square root of 2gh. So, square root of 2gh right here gets me 19.8 meters per second. And then I can use that as my V max, which means my amplitude turns out to be 14.1 meters. And so you know, in this particular case, that you want to make sure that your bungee cord is at least 34.1 meters above the ground. Right? By 34.1? If you put your bungee tower 30 meters above the ground and you have a 20 meter bungee cord, this thing is going to stretch a total of 34.1 before that person turns around, right? So you definitely want to be more like 50 meters above the ground so that you have built-in safety margin.
What age did he put in there? The 20?
20.
Okay.
Right? How fast is it going? When it falls 20 meters? Any other points of confusion? I'm sure there's plenty. But let me give you some more tools. Remember energy? Trying to forget it? Springs, bungee cords, store potential energy. When I pull down on this spring, I'm holding it here, the spring is full of potential energy. And what does that potential energy want to do? Turn it into kinetic, right? It wants to get rid of that potential energy. The potential energy in a spring, called elastic potential energy. Let me see what symbol your book uses. They use use PE elastic, okay, is 1/2 kx squared. Now, there's several ramifications of this statement right here. First of all, notice that when you stretch a spring a certain amount, and then you stretch it twice that amount, how much did your energy change? If you stretch a string twice the amount it normally stretches, it doesn't double. 4 times. That position, that distance is squared. If you do 3 times the stretch, it's 9 times as much energy stored in that spring, right? So watch out for that squared value. The other thing is, the energy that something has, the total energy something has, could consist of linear kinetic energy, rotational kinetic energy, gravitational potential energy, and elastic potential energy. Now, quite often it does not have all 4 simultaneously. If you have a rotating spring falling somewhere, you are in big trouble. Okay? Usually it has like just all the potential energy or something like that, right? And then that potential energy is going to get turned into something. But for completeness, an object can have all these different kinds of energy adding together to be its total energy. And when you do conservation of energy problems, you should be considering, again, not just kinetic energy, but rotational kinetic energy. Not just gravitational potential energy, but if there's a spring, that spring could be storing potential energy as well.
So a yo-yo.
Yo-yos are awesome. They're so cool. And we are not going to talk about them. Because, they're rotating and falling. Oh, it's so good. And some of them have circular springs in them. Oh, it's so exciting. All right. Where is the potential energy of a harmonic oscillator the greatest? Top or bottom at amplitude?
No, just the top.
Not just the top, it's also the bottom.
But is it negative?
No, because it's distance squared.
Oh, yeah.
Right? Okay. So even though this is positive A and this one's negative A, you're squaring those things, right? So the amount of energy is going to be the same. So whatever energy it has stored down here is exactly the amount of energy it has stored up there. Okay? Where is the kinetic energy 0 for an oscillator? At equilibrium. At the end. It was a really good spring. It was a really, really good spring break for me. Right here at the end. How do you know the kinetic energy is 0 at the end? It's where it stopped, right? It's not moving. Okay? Where's the potential energy 0? At equilibrium, where it's moving the fastest, right? So a simple harmonic oscillator, like a pendulum, converts potential energy into kinetic energy back and forth again. We can actually take advantage of that idea in looking at the total energy of a simple harmonic oscillator. Again, it can consist of the energy it has because it's moving, kinetic energy, and the energy it has because the spring is compressed or stretched. But I have another way to write down that total energy. The way I've written it down is what the energy is at any point along its motion. Whatever x is for that given spot, right? And that v. But I can write down what the energy is at the ends, or at the middle if I wanted to. I'll do it at the ends. Another way to write the total energy is to do 1/2 k a squared, where I've put in the amplitude. The amount of energy this oscillator has is constant. If it had 10 joules down here, it's got 10 joules at the top, and it's got 10 joules in the middle, and it's got 10 joules halfway in between the bottom and the middle. because energy is conserved. It's going to be the same total energy no matter where it is. The only question is, how much of that 10 is tied up in kinetic energy versus potential energy, right? It's trading back and forth, but the total always remains the same. And in this case, in the general case, 1/2 k times the amplitude squared represents the total energy, as well as 1/2 mv squared and 1/2 kx squared. So I can set those equal, since they're equal to the same values. And this is looking bad, but I can get rid of one thing right away. Stinking halves, I don't want them anyway. What can I solve for? Oh, let's solve for v. Solving this for v. You get ka squared minus kx squared is equal to mv squared over there. Oh, let's get rid of the k. Let's not get rid of it. Let's pull it out. A squared minus x squared over here, right? Just kind of trying to clean some stuff up. If I'm solving for v, I want to get rid of m. There we go. So let's write this, turn it around over here. So v squared is now equal to k over m, a squared minus x squared. And take square root to get v. What's the square root of k over m? Boom! Right there. What is that? I wowed you with mathematics. Or in other words, I confused you with mathematics. Right?
What is that?
What does it say? It says that we can find the velocity of that oscillator if all we really know is its position. I mean, granted, we need to know omega and amplitude as well, right? But this is velocity at any place. What's missing? Time. There's no time in this. And that saves a whole lot of problems. Okay? So if you want to find out how fast something is going, use that. If you know where it is, right? So let's check. We better check this result. This is like too good to be true, right? So let's check it. Let's make sure it works. Okay? What's some obvious values we can put in for x?
2.
2? What's a simple value we put in for x?
No.
Simpler than 1. 0. 0 is an easy thing, right? Makes all problems go away. Just take your life, multiply both sides by 0. Put 0 in there. What do we get?
0.
Well, we get the square root of a squared, which is what? A. And what's omega times a? Look at the toolbox. It's the maximum speed. Wait a second. This thing has its maximum speed when its position is at the equilibrium point? Okay. What's another obvious choice for position? Something like, where do we know something about this? We know at the center it's got maximum speed, right? Okay. But what about the ends? What do we know about the position here? It's A, right? How fast is it going at this point? 0. Is that what that says? When I put A in for x, I get a squared minus a squared. What's that? What's the square root of 0? What's 0 times omega?
0.
I like it. Right? Seems to be working. And since it works at both ends, I'm assuming it'll work all the way in between. Because that's exactly what it does. So, you'll want those boxy things, right, in your toolbox as well, right? Mine's split across screens, but make sure that you get those two that are there in the boxes into your toolbox. Of course, they're up on Dropbox as well. Right here, I think. Simple harmonic motion. I'm trying to decide which example I want to do. I've got two. I've got time for one. We'll do this one. Hey. Again, simple harmonic motion problems tend to either overwhelm you with information, like give you a lot of numbers, right? Half of which are like red herrings you're not going to need. Or it seems like they don't give you enough information. Like, I got the mass, and I got a force, and I got a distance, and I'm supposed to find what? Everything. Spring constant, frequency, maximum speed, maximum acceleration, total energy, speed and acceleration of the object at certain positions. Right? That's like a ton of stuff for not very much beginning information. But remember, the key to your toolbox is, let's see if we can find omega from this information, right? Do we have a mass? Yeah. So omega can be found by finding the spring constant and dividing by the mass, taking square root, right? It can be found if we somehow were given the period, which we weren't, right? But what other sorts of information have we been given in this problem besides the mass? We were given a force of 20 newtons and the distance that it was stretched, right? So what are we going to use there? Oh, the Hooke's law, right? Okay, Hooke's law. And to find that spring constant, I take that force and divide by that stretch. The force, 20 newtons. The stretch, 0.2 meters. Oh, okay, wait a second. I think I can do this in my head. That's 10. And then 10 to, that's 100. Did I do that right? Here's hoping. Again, don't use the negative sign, right? Go for magnitudes. The negative sign is helping you remember a direction, but we're not dealing with that right now. Okay? All right. So I've got my spring. Oh, that means I've got omega, right? It's going to be the square root of 100 over 2, which is the square root of 50 radians per second. So there's my omega. Oh, they don't want to know omega. I'm not going to box that. But they did want to know k. There's my k. Frequency. Omega is equal to 2 pi times f. So my frequency is going to be omega divided by 2 pi, which is the square root of 50 over 2 pi in hertz. I'm leaving it as the square root of 50 because I'm too lazy to get my calculator out. We found spring constant. We found V max. How are we going to find V max? Omega times A. Do we know the amplitude? It's pulled from rest to an initial position of 0.2. What's the amplitude? 0.2. Okay. So I take my omega, square root of 50, and multiply by 0.2 meters, and I get a Vmax of, I didn't write it down. Nope, don't have this one in my notes. Have it in my other book of notes. So whatever that number happens to be. How do we find the A max? It's omega squared A, which is going to be 50 times 0.2, which is going to be 10. Right? 2 times 2 is 100, times 0.1 is 10. Meters per second squared. E total. I could do 1/2 Ka squared. I could do 1/2 mv max squared. Doesn't matter. I'll do that one. It's going to be 1/2 times 100 times 0.2 squared. Again, whatever that turns out to be. Have you noticed something about me and these equations? I'm not using any notes. Okay, the problem I've got in my notes is totally different than what I'm doing right now. I've memorized all these equations. Why? You know me in memorization. I hate it. Why have I memorized these?
You've done it a lot.
Not only have I done it a lot,
It comes up in physics a lot.
but it is our go-to. And so therefore, if you have these equations in your back pocket, no matter where you are, you can figure out a lot of stuff really quick. I'm not saying you have to memorize them. I'm just saying this toolbox is awesome. It really is. Because a lot of stuff falls out of it that would normally have to float around in your brain. Find the speed and acceleration of the object when it has a certain position. Oh, I know how to do that. I just found that one, didn't I? I know the position is 0.67. I know the amplitude. I know omega. Done. How do we find the acceleration as a function of position? Well, that was one of the first things I gave you. I had a minus sign on it, but since they're just asking for what it is and not its direction, I don't have to worry about it. So we had our Vmax, we had our Amax, we had our total, we got our V, we got our A. I've managed to find everything they asked me for by really just kind of finding omega, knowing what the amplitude was, and running with it. In my experience, students, they come to me after learning simple harmonic motion and they go, oh my goodness, why hasn't this class been this easy the entire time? And my answer is, simple harmonic motion is easy because you've been through 12 weeks of absolute torture, right? And you've gotten to a point now where you've either just totally given up everything and you're just willing to let it go, or you're going, oh, okay, I understand some of the ideas behind here. I might not be getting all the connections, but wow, this is, it's pulling together so many different things from kinematics and energy and what we know about position and things like that, that it becomes an exciting time. And dare I say, an easy time. I don't have a lot of time to go into the simple pendulum. Back in week 2 of this course, that was forever ago, wasn't it? We did our first lab together, first real lab with the pendulum. We had little photo gates and we had you measure little g. Remember how nice and innocent your life was back then? We gave you the period of a pendulum. And it looked like that. And we said, well, don't worry about the 2 pi. We'll explain it later. Well, it's later. Where does the 2 pi come from? It's a circle. Simple harmonic motion. Circles, pendulums, masses on springs. The period of a pendulum can be found by doing an absolutely amazing derivation that I would love to show you, but I'm not going to. Because it would waste your time. And you've already seen me geek out on math today. Suffice it to say that a pendulum does not have a spring in it, right? So why is it that physicists get so excited about explaining just about everything, even though most things don't have springs in it, right? Like stock market, right? Physicists get snapped up by trading companies, investment companies, to model the stock market. Because we understand complex systems that have periodicity in them, and we know all the mathematics that surround them, and we can program computers to predict what's going to happen. It doesn't happen with perfectness, but we can get a pretty good idea. In Wall Street, they're called quants, the mathematicians and physicists that model the stock market. And what you do is you take a system that seems to be oscillating or has oscillating type features, and you look for the parts of that system that are acting like a spring. In the case of a pendulum, it's the length of that thing and how the mass on the end of that string is being influenced by the planet that it's near. Those things have a spring-like quality to them. And so you find spring constants for things that don't have springs in them at all. For circles, no springs there, but we can write down radius and mass and amplitude in ways that behave just like spring constants in the equation. For planetary orbits, we can do exactly the same things. For car bumpers, you name it. A physicist will go out and find a spring constant for something that doesn't have a spring in it. And why would this be important? Let me give you just one example from my own experience. I had a friend in high school who was an amputee. Okay, had lost his leg from just above the knee down. Okay, and we knew, right, that he had a prosthesis, even though he wore pants, he never wore shorts, because of the way he walked. Right, when he'd walk, right, there would be this sort of strange. What's it called? What's the word called to describe how a person walks? Their gait. G-A-I-T. Right? Okay? So a normal human gait has this sort of evenness and periodicity to it, right? But my friend's gait had sort of this, it was doing one thing on one side and then one thing on another side. And the reason for that is because human legs are pendulums, right? So when you walk, it's actually a double pendulum. You've got a hinge here and you've got a hinge up here, right? But we could just think of it even just as a simple pendulum right here, right? Okay? And this motion right here determines your gait, the periodicity and frequency of your footfalls. The mass of his leg was different down here than the mass over here. It changed the moment of inertia of this leg compared to his regular leg, right? So you had two different moments of inertia on either side. Well, it turns out that pendulum, simple pendulum, mass on the end of a spring, has a period that is written like that. But if you have a physical pendulum, like a leg or a bar, right, something that's where its mass is extended, you don't have to write this down, I don't think. If you do, it's in your book anyway, okay? You can find out what the period of a physical pendulum is, okay? If you use L, the distance to the center mass of the physical pendulum, moment of inertia, weight of the pendulum, so on and so forth, you can find out what the period of a physical pendulum is. Well, around about junior year of high school, my friend went from walking with that funny gait to all of a sudden walking normal. Right? He was like over the summer, like, whoa, what happened? Right? And he pulled up his pants and he showed us the new prosthetic that he had. He'd finally grown enough where they could make a prosthesis that was guaranteed to not, his body wasn't going to change too much more. And so they were able to make a custom one that was tailored to the natural frequency his legs had for his gait. And so unless you ran up and kicked him in the shin, you wouldn't know that he had a prosthetic. It was tailor-made for him. In the Boston bombings, there were many, many horror stories about people that not just lost their lives, but lost limbs in that bombing. There's a particular story that came out. One of the runners that crossed the finish line had her leg torn off just below the ankle, and she danced in the Boston Ballet. And so a student group at MIT decided in the robotics division that they were going to make her dance again. And so they developed a prosthetic ankle, right, that replaced her foot and her ankle, because all she had was a stub down there. And this thing was tailor-made, and they used simple harmonic motion and a whole host of other things with robotic servos and things so that she could dance the ballet again. And she was back in the ballet. This is like, we are living in an age where we have the technology to bring quality of life back to individuals that have lost limbs for a variety of reasons. And it comes down to understanding the biophysics of what's going on, the periods that are involved in human motion. Simple harmonic motion, it becomes really complicated really fast and not so simple, but in the end, it impacts lives in an incredible way. Not only from the safety of your automobile and your car, but to medical fields as well. I could keep going. There's millions of examples now of how awesome this tech is and how it all goes together. But we will talk more about that tomorrow and do the test redemption tomorrow as well. Don't miss lab.